So I'm going to speak today about the detection and correction of silent errors in the conjugate gradient algorithm. So I'm going to briefly explain what silent errors are. And I must warn you, I don't have a slide about the conjugate gradient algorithm because I was assuming that everybody in the audience knows about the conjugate gradient, right? If it's not true, please raise your hand. No? Okay, fine. Good. Well, I don't know how to use short now. So anyway, so that's the outline of the talk. So, today's supercomputers have more and more computing elements, processing elements, and therefore, what we call them processors or cores or GPUs or anything else probably in the future. And so it's more likely than before that there can be some hardware failures when you're running a code on these machines. So some of these hardware failures, they can cause your code to crash. So in that case, then if you have not saved some data, then you have to start again from the beginning. But there can be also what is called silent errors. Whoops, sorry, excuse me. Silent errors, which in fact may cause a floating point value to be changed to a different floating point value, which is valid also. Okay, and this could happen, for instance, from cosmic rays, for instance. Or cosmic rays are not the main cause, but the secondary particles that are coming from cosmic rays can eventually hit the silicon chips and make some kind of silent errors like that. So this kind of errors, they may have a strong and, of course, negative effect on the output of your code. And probably the answer at the end will not be right. But the problem is that you don't know that something has gone wrong. And so it's going to be more and more important for the resilience of codes to be able to detect these silent errors. Okay, so the most basic technique that can be used for fault detection is to do some redundant computations. So these techniques are very general, and they are usually called double modular redundancy, DMR, or triple modular redundancy, TMR, if you're doing the computation twice or 3 times. Okay, but of course that's it's something which is costly and which may be impractical in many cases. And so another interesting class of methods were developed later, which are called ABFT, because they use, in fact, they want to exploit the knowledge we have, or we may have, about the numerical methods which is used. So it is algorithm-based fault detection. So you have an example here in the early 1980s. People describe an algorithm which was capable of detecting a single silent error in a matrix multiplication. And for doing that, they were using row and column checksums. Okay, so here we would like to solve a linear system, say x equal b, where the matrix A is a real, symmetric, positive definite, with the conjugate gradient algorithm. And there were some people who looked at this problem, detection of silent errors in the CG. So they proposed, some proposals were to monitor the residual norms from one iteration to the next, or in the average when looking at some m last iterations. Okay, but you have also some people propose to use the check of local orthogonality. Whoops. Check of local orthogonality. For instance, you can check this pk -1 apk, where pk is the descent directions. And of course, in exact arithmetic, this must be 0. So there was a proposal to test that, because if it's not 0, then you could be an error. But of course, you have to know how tiny is tiny and so on and so forth. And it's not so easy. And another proposal was to compare the computed residual vectors in the algorithm and the true residual, which is the b minus a xk. Of course, but in that case, you have to compute the true residual norm, which is not so, that's a little bit expensive. And monitoring the residual norms may not be so easy because you have some cases in which the residual norms in CG are very oscillating. And so it's not really easy to monitor that something is going wrong, actually. So I was reading some papers about this kind of proposal for detecting this error in CG and say, well, maybe eventually we can do something else. Okay. But first, let's look at what is the effect of silent errors on CG convergence. So in this work, I simulate the silent errors by bit flips in the output of some CG steps. Okay, so just take the result, for instance, of a dot product, and you flip a bit in the output of the dot product. So I'm using IEEE double precision, floating point arithmetic. So the Mantis has 52 bits that I number from 1 to 52. 1 is the rightmost bit. The exponent has 11 bits. That is the bits 53 to 63. And the sign bit is bit 64. And intuitively, you may think that if you're flipping low order bits, this should have less important. It should be less important than flipping a bit in the exponent field, for instance, or in the sign. And it's also likely that if you flip a bit when CG has almost converged, this is probably less dramatic than if you have an early bit flip. And this is almost the same kind of thing that is reminding, but the people were doing in this so-called relax method when you are allowed to do the matrix vector product approximately, right? There were some papers written by Valeria Simoncini and Daniel Schild about that. Okay, so let's look at some experiments. So we're going to check what happens when you're solving the system with this matrix BCSS TK01. It's a small matrix of order 48. The condition number, which is almost 10 to the 6. But even if this matrix is of order 48 and we are not using a preconditioner, so we have to do almost 200 CG iteration to reach the maximum attainable accuracy. That is the smallest value of the true residual norm. Okay, and I'm using a zero initial vector. And so here you are, an experiment. So I'm flipping a bit on the output of this dot product while you compute the square of the norm of the residual vector. So I'm doing that at iteration 50. I'm flipping only one bit. So I'm flipping bit 7, which is a low order bit 35, and bit 61. And you can see if you flip the bit 7, the blue line is what you obtain when we don't flip a bit at all. And when you flip the bit 7, you have a little perturbation, but not too much. And more or less, you converge in the same number of iterations. But when we flip bit 35, then you have a delay in the convergence. And maybe eventually you will converge later on, but you have to go on for many more iterations. And when you flip a bit 61, which is in the exponent field, then it doesn't converge at all. Okay. And now, this is one more experiment. When I flip bit 10, 20, 30, 40, 50, 60. Okay, so you see that with bit 10 and 20, it's almost the same as when you don't flip a bit. And these ones, in fact, are going to converge in many more iterations, but they will converge anyway. But the one in which you flip a bit in the exponent field does not converge in 1,000 iterations. So flipping bits like in these experiments, in fact, show you that it's useful to be able to detect that. right? And here you're, I'm flipping bit 60 at iteration 110, but in the output of different steps in CG. And you can see that in most cases it doesn't converge, or eventually it converges in many, many more iterations. So what was the idea to try to detect that, in fact? So I was considering a formula that was derived by Youssef Saad in 1985, if I'm right. And I used in a paper in 1987, just for the sake of trying to introduce more parallelism in CG. In fact, I was using what I call the predictor corrector technique. So in CG, you have the residual norms which satisfy this relation. So Rk are the residual vectors. This alpha is one of the CG parameters, which is the ratio of the norm Rk minus 1 squared divided by Pk minus 1 transpose A Pk minus 1. And you have the product, the matrix vector product, Apk minus 1. So if you use that, you can show you this relation, actually, which alpha k minus 1 square times this dot product, which is the norm squared of Apk minus 1, is equal to the sum of these two norms at two different iterations. And so in 97, I was using that to predict the value of Rk, the norm of Rk squared, before having computing Rk, right? So I'm claiming that if this relation is not satisfied, then you can say that if you have silent errors, this relation is not going to be satisfied, right? And that's what I'm going to check to see if I have a silent error. Okay, so in fact, I'm using this ratio, dk, because I'm using a relative difference. And to avoid having too small quantity in the denominator, I'm using the square roots of the left and right-hand side of my equality. And if I plot that without any bit flip, I have this curve. And you see this is 10 to the minus 15, 10 to the minus 14, 10 to the minus 13. So you could have expected that you will get the machine precision, but it's not the case, in fact. It's small, but it's not the machine precision. Okay. And why is that? So if you look at what happens in finite precision arithmetic, you have the residuals which give in the descent direction, which are given by this. Now this is the computed quantities, and now you have this perturbation due to round-off errors, which can be bounded by these relations, where u is the round-off unit, and these two coefficients, in fact, they are positive and they can be bounded because the ratios of the residual norms and the descent direction norms are in fact bounded. So if you look at what happens to the relation I'm using, in fact, now you have these perturbation terms. Okay, so this one is small, that's for sure. This one is going to be small also, because this is small. This is going to be small if CG is converging fast. But the problem comes with this one. So in exact arithmetic, the residual vectors are orthogonal, so this is 0. But it's not 0 in finite precision arithmetic. And when you take the relative difference, then you have terms like that. And this is the explanation why you do not get the machine precision level. But anyway, if you want to use this term, then you have to compute one more dot product, which is more or less expensive. So I'm not using this term. So I'm just using the basic relation. Okay, and now is what happens to this relative difference decay when you flip bits 7, 35, 61 in the output of Rk, the dot product of Rk with itself at iteration 110. Okay, so this the blue is what you get without any bit flip. And you see when you flip a bit 7 and you have this curve, so you are not going to be able to detect that But it doesn't really matter because it's harmless, as we have seen before, because you get the same number of iterations, more or less. But when you flip a bit 35, you get this curve, and bit 61, you get that one. So clearly you see that something had happened at iteration 110, and you have to do something. Now if you flip the bit 10, 20, 30, 40, 50, and so on, you get this result. So the larger is the bit number, the larger is the value of this ratio decay. And of course, when you flip the bit in the exponent field, then you get this very large value, which is close to 1. Okay, so how do we detect that? Let's say that we have a given threshold. Then we say that we have a fault at iteration k if this decay is larger than this threshold. And of course, the problem is to choose the threshold. Well, okay, so people could say that, okay, well, you can have also a fault when you are computing decay, right? Eventually. But this computation of decay, in fact, it just involves a few scalars and a very few operations, so you can do that redundantly 2 times or 3 times and compare the results. That's not a big issue. And when you're using a preconditioner, so you have to compute this vector zk given by this solve, then the relation becomes this, in fact. Instead of looking at the norm squared, you have this dot product of the vectors rk and zk, and you can do the same thing, more or less. Okay. So now that we have a way to know if there was a silent fault at iteration k, then we can implement a recovery procedure, right? See, you assume that you have at hand the values of the CG vectors and the coefficients at the beginning of iterations k and k minus 1. And if you detect a fault at iteration k, then you go back at the beginning of iteration k minus 1, because the fault could have been happening at the computation of pk minus 1 at iteration k minus 1. So you detect you have a silent error, and you go back at the beginning of iteration k minus 1. So let's see if it works. So here I'm flipping a bit 60 in the output of this dot product at iteration 110. I'm okay here, and I'm applying my recovery procedure. And there is a delay here because I did not update the iteration number after the recovery procedure. So I'm going back to some iteration k minus 109 in that case. But I did not update the iteration number. And you can see that you get what you expected to get back to the normal convergence of your iteration. Okay, so you can also use the predictor corrector technique that I was using in 1987. In fact, when you're using a preconditioner, then you predict the value of this dot product to compute the second CG coefficient. But if you just do that, in fact, this method is unstable, and so you have to recompute the value of this dot product at the end of the iteration for the computation at the next iteration. And if you use this technique, then you avoid one of the 2 solves with the preconditioner that you have because of the detection process. And if you do that, this is a matrix which is KUU, which is a matrix of order about 7,000, with a condition number of 1.6 10 to the 4. And I was using a complete Cholesky preconditioner. And you can see the relative to residual norms. I'm flipping a bit, and actually it's in RKZK. That's a typo. At iteration 15, I applied a recovery procedure, and we can see that it's working nicely also. Okay, so this method seems to work to detect silent errors in CG, to correct them. The detection criterion is simple. It's cheap to implement. And many numerical experiments that I've been doing show that it's robust and reliable. And one of the advantages over some other methods is that it's simple and that the check for error, you can do the check at each iteration, in fact. So if you have a silent error, you don't lose too many iterations, because sometimes people are doing some checkpoints every 100 iteration or something like that. And if you have to go back, then you lose a lot of computing efficiency. Okay, so here are the references. So that's a Youssef paper in 1985, my paper about predictor corrector method in 87. And in fact, this method of doing prediction and correction, it was almost not used by anybody for 30 years. And after 30 years, it was reconsidered by Tyler Chen and Erin Carson. So they changed the name of the method. They call it predict and recompute, which probably is a better name than what I used before. And in fact, they extended this kind of ideas to many of these new pipeline variants of CG that people have been developing for increasing the parallelism. And many of these methods are not so stable anyway, or they have a bad maximum attainable accuracy. And if you use this kind of ideas of predicting things and recomputing, then you get much better results. And this paper also is interesting to look at because they do some sort of statistical study of the effect of what they call silent errors, soft errors, but they do a statistical study of what happens when you have this kind of errors in CGS. It's quite interesting to look at that. Okay, so let's go to the last slide. Actually, so I would like to say happy 80.10 birthday, Claude. And as you can see, this picture was taken in this place at CERM in 2007. And we were playing pétanque, you know. So were you still able to play like that? I don't know. It was a very sunny day, you know. I said, oh, okay. So happy birthday. And thank you for your attention.
Thank you very much for a nice talk and a fantastic picture, in fact. I'm impressed.
Yeah, you can see the ball, actually.
Yes, exactly. That's impressive.
But I'm sure that if we want to play pétanque now, the balls will have to wear a mask. You know, so, I don't know. Probably.
Are there comments or questions? Yes? Uh-huh. Well, it depends. Can you repeat the question?
Yeah. Oh, well, okay. The question from Youssef was that what is the overhead of this detection method? And well, in fact, if you do not use a preconditioner, there are almost no overhead because you just have to compute one more dot product, okay, per iteration. But if you use a preconditioner, then you have seen that there is the precondition is involved in this relation, and eventually you will have to do two solves with the preconditioner at each iteration. But if you use, so you can do two things. Either if you have a preconditioner which is L transpose, then you can precondition your system at the beginning and run without any preconditioner. But if you don't want to do that or you cannot do that, then you can use this predictor corrector technique, and then you will have only to have one solve with the preconditioner at each iteration. So the overhead is just one more dot product.
So thank you again.